talk about the MIRI current calibration on behalf of essentially the entire MIRI team. Everybody's involved in one way or another one in the imager, MRS, LRS, coronagraphy detectors, absolute calibration, wide-field leadless spectroscopy, and time series observations. Everybody essentially in MIRI is doing some work on calibration. And I will briefly go through the instrument overview, go through the observing modes, and then I touch on some of the highlights of the imager and the coronagraph. They are part of the same setup. The medium resolution spectrometer, the low resolution spectrometer, and LRS leads to two modes that we are using all the time. One is the wide-field leadless spectroscopy. That is just the beginning of it. And of course, the leadless spectroscopy has been a very powerful tool for doing time series observations. So we'll touch a little bit on that as well. If you click on any of those links, you will get to some of the classical MIRI information. That's the MIRI instrument. And if you click on that one, you get a calibration status. So you can always, and that has been one of the big efforts by the JWST team, is that to have all the documentation available for the public in JDocs. And so you can always check. We have, just like NIRCam, we have published almost everything that comes in referee journals. We have at least 2 manuscripts on the calibration for the imaging for MRS. There's one coming for LRS. There is also some high precision astrometry, photometry, and these are just a sample of the many publications that we have, technical publications that we have for MIRI. Again, if you click on the link, you get to our lovely ADS public library, and you can go through the several papers that have been published by the MIRI team, but locally and of course working with the European consortium. MIRI is, NIRCam, the beautiful center of the instruments. I mean, it's a little bit of the side, right? And one of the issues that we need to take into account, and it's one of the works, and Anton mentioned it again, is that we do need to be more careful with, for example, distortion correction. So this is the full array that has the coronagraphs, and the little corner is the MRS that has 2 detectors, and it's the medium resolution spectrometer. So the observing modes are the following. We do direct imaging. We have 9 filters covering from 5.6 to 25 microns. There is a coronagraph that has a LEO, the classical LEO coronagraph at 23 microns. And then we have 4 quadrant size masks at 10, 11, and 15 microns, essentially. We have an IFU, the intergraphic unit, which is MRS. We cover from 5.9 to essentially from 5 microns to 28 microns. Also, the throughput at the longer wavelengths is complicated, not as good as one we liked. The low resolution spectrometer, we have, again, the ability to do aerial spectra from 5 to 14 microns with a slit. In the time series observation, we can use essentially the same setup, but in the slitless mode. And as I mentioned, one of the modes that's going in cycle 5 is the wide-field leadless spectroscopy that relies, again, on the low resolution spectrometer, but allows you to look at multiple sources. And this is, you have seen this many times, so all of you that have JWST. Again, this is the MIRI full array, the MRS. And here on the right, shows you where the slit is for the LRS spectrum. It shows you where it comes for the LRS slitless spectroscopy, the mask again. And for MRS, we have the guides, channel 1, channel 2, one detector and the short detector, and then the other 2 channels and the longer detector. And of course, we have 12 subbands going from short, medium, long for each channel. So it does take a lot of calibration through that. And Tom showed a very nice plot. I didn't want to show all the calibration plans that we have. But this is what we just presented recently for the Web Mission Office, which shows the kind of things that we'll do for calibration in cycle 3 and the current cycle 4. And so just we take DARs, flats. We do have thermal anneals, unlike the near-infrared detectors. We also characterize the last frame. We look at the background. We look at the throughput. We look at the dispersion, the PSF. And so a lot of things that aiming to have the most accurate calibration of the different observing modes. If I won't touch, this is again come from JWeb's information that tell you again some of the things that I can measure of the field of view, the wavelength range, the resolve bit power, and so on. So let me touch on the imager. This is on the right is a lovely image of field that comes from commissioning. This is 7.7 micron image, and on the left it is just like NIRCam. We also have subarrays with shorter frames that we can observe brighter things. We have subarray 64, so 128, 256, and that's the number of pixels, of course, 64 pixels, 128 by 128, and the bright sky is a bit bigger than that. And all of those things, so the mask for the coronagraph, and all of these pieces of the arrays to be calibrated. This is from the calibration paper for the imager and the coronagraph from Carl Gordon, and it's just to show you what the PSF look like. And this goes from 5.6 microns to 24 microns, and includes also the neutral density filter that is used a lot in the photographic observations on target acquisition in particular for very bright sources. So there is also an effort that we use, since it's used and get light, that filter that is being calibrated. These are at the bottom the PSF that go to the coronagraph mask. And also there is an effort to calibrate those. On the right, there is this again comes from the article. This is a typical series of calibration that we do for MIRI, where we take the different filters for the imager, and of course also we try to do it for as many subarrays as possible. And we have not only solar analog observations, but also different type of objects. Now, our absolute automatic calibration, we believe is just without target acquisition. It's about 0.1, 0.2 arc seconds. This can be refined afterwards because in many cases one can use a Gaia catalog and a tool that we provide to the users. It's called TweetRec, and then you can improve the calibration in the astrometric calibration to 0.1, 0.03 arc seconds. The problem for us, for MIRI, is that we discovered later in commissioning that, indeed, after even a lot later the commission, that we have reduced count rate effect. And so what we measure in the beginning is different from what we measure now. And I'll show you in a minute some of the plots. And so, so one of the things that we need to do is trending of this essentially count rate time dependent function reduction. This affects mostly the longer wavelength fit. In the table that is on the right shows you more or less the effect that we think is affecting in terms of function of time. So let's say from commissioning to now, 24 microns, there has been a reduction of the count rate for about 26%. Now we can correct this in the pipeline, and once that is corrected, the uncertainties and the automatic calibration is better than 1%. But it's one of the challenges of our calibration, automatic calibration. As Anton mentioned, since we have the subarray, we also want to tie our calibration and compare what we get on the full array with subarray. There is some dispersion. We also check that this was the behavior as a function of dithering of each of the position. But overall, as you can see, the scale is this is one essentially. So the calibration, even for the subarrays, is quite good. For the other plus minus 50%. The image image count rate reduction. This is one of the first plot, again, provided by Carl Gordon. This is the fractional change. And this is essentially an exponential plus a line. And from the time of the commissioning until now, as you can see, things have decreased as a function of time for the longer wavelength filters. Once that you go to 11 microns, 10 microns, 7 microns, 1.6, it's essentially disappears, right? Negligible. But it's one of the concerns that we do. This is a more recent plot, again, of the reduced count rates. It looks very spectacular, particularly for the longer wavelength. But we do have a model. The model is just to correct the observations. So once that they are corrected, as I said, we believe that photometric calibrations of the order 1%, 1-2%. The coronagraph is part of the imager, and again, because of the issues with the reduced count rate, and particularly at the longer wavelengths, 15 microns, 22 microns, we believe that the percentage is of the order of 3%. The automatic calibration has to be very good because we have to place the targets behind the masks. And so the precision is so the order, within 5 milliseconds and consistent. How we do that? That is done through target acquisition. This is what I call the Russian doll model, where we go to the position that blocks in general a very bright source. That's what you want to hold. And goes from there to an initial target acquisition, then another target acquisition, region of interest, and then finally behind the mask. And that's one of the ways that we can reach accuracy in the position of the target behind the mask. And what can you get from that? Well, I wanted to show some of the highlights. This comes from guaranteed time observation from Anthony Boccaletti. And this is HR 8799. And you can see what you can get is once you block the source, you can actually see exoplanets. And in the longer wavelengths and inner disk. So it works quite well. Moving along, one of our favorite instruments for the community, that's a medium resolution spectrometer. It's one of my favorite movies. I don't know if you have the sound. This comes from our partners, European Space Agency, and I like it very much because it does have MIRI for MRS, and it's coming the light. There it goes now. Okay. Comes the light, comes reflected. It's disperser. It does tell you how complicated are these instruments. There it goes. Goes to the diffuse, the electronics. Finally, it goes to the detect. And let me stop it just briefly there. So there you go. So this is the way that the MRS works. The integrated units, those are the detectors. And from there, we can get fantastic spectra from essentially 5 to 10 micron. So the wavelength calibration for MRS. The wavelength calibration is in nanometers. Let me remove myself, blocking my own window. In nanometers is of the order of 0.1 nanometers at 5 microns, about 4 nanometers at 28 microns, 20 kilometers per second, between 9 and 27 kilometers per second. So not bad for a medium resolution spectrometer. The photometric calibration, we compare the accuracy of the absolute flux calibration of MRS with that of the imager, and it's between 7 and 21 microns of the order 1%. The throughput channel 4 decreases, you will see in a minute. So that makes it more complicated. The comparison, the uncertainties are large. But it can be done. And one of the tricks that has been used by David Law, or original MRS lead, was to use a longer wavelength, the main an asteroid Italia, and also a single tail like this, and that ties together the calibration for the absolute flux calibration. I'll show you in a minute. And obviously, this is an eye view, so people also care about the standard source calibration. And one of the tricks that David used was to compare with actual observations disk of planets, like that's Saturn, for example. And so the calibration that is obtained from, for example, the Cassini composite infrared spectrometer and the Voyager spectrometers match quite well, 5% of the MRS calibration for the standard emission. The automatic calibration without target acquisition is of the order of half a pixel, 45 seconds, and radial. So many times we recommend the service not to use target acquisition for MRS, only if you want high precision and position the source on the same pixel, because the automatic calibration is very good. This is the part of the photometric calibration. This shows the relative calibration of different observations for a star compared to 10 lakh, which is one of the main calibrators, which is this one. And so the average of the solid line is actually marked with 10 lakh is, and the dashed line shows you the average from the different other sources that have been observed for the calibration. At the end, you get something like this. There is a CalSpec model that is again the model for that type of star, for O9b in sequence star. It looks fantastic. You look at the observations with the model. When you look at the more details, lambda squared F nu, then you can see the slight difference. And the slight difference comes because we use the average from all the stars to the calibration. And a longer wavelength, as I said, we use the tie the calibration with the main belt asteroid and a circumstellar disk. And again, you look at least in the F nu wavelength plot, it does very good. And when you compare with real sources, this is one of the observations against HR 2787 that compares with the expected location of the hydrogen lines, and you can see it's quite impressive. Very worthwhile. And the photometric calibration, again, one can compare for the different spectral types of the sources that are observed. And clearly there is still some, if you want, color dependent. But again, when you look for example, when you compare it with O dwarfs, A dwarfs, and G dwarfs, things in the average look very well, but there is still slightly difference for different spectral types, right? So there is a systematic difference for certain stars, and it's one of the things that we're investigating and trying to understand. As mentioned for the imager, this was the original plot created by David to show that the MRS count rate was decreasing. So again, that's a function of time. We have this sensitivity was going down. What does that look like? Well, this is what a comparison between May 2023 of one of our calibrators, SMP LMC058, and so the red line is May, the dark line is 2022, and so you can see the difference. So once you do the correction in the pipeline, which is one of the things that's done now continuously for the data, you can match perfect. So it's a pain, it's a pity, but we deal with it. It can be correct. What kind of science you can do? Well, you can look at things as C7 point, and you can look at AGS and claim that because the cosmic time you don't see any variability, and so you can get fantastic spectra and positional lines even very high. MRS, LRS. This came from Greg as well, the LRS split. This is a typical image of the LRS split. That position is again for the target acquisition. This is the split. Spectrum look like. There is the acoustical pattern, is one of the things that affects some observation also of the imager when it falls into the array, and several area rings. It's also the kind of things that one has to be concerned when extracting the spectra. For LRS, the Webben calibration is automatic calibration. It's of the order of 1 to 2%. Really, we did very good, but we have some issues again at the shoulder longer awareness. At least for observational set of this, it's essentially the same source. We know it can be repeated within 1% for both split and linear observations. For the Webben calibration is a little bit tricky for LRS. It's a low resolution, and so the errors are relatively large for range of the shoulder awareness below 6 microns and about 12 microns. I'll show you in a minute. And this is one of our classical plots that shows the difference expected compared to the wavelength of our calibration lines in nanometers. You can see there is a range which is the order 20. Things behave very nice across wavelength, but at the shorter wavelengths and at the longer wavelengths, the difference is a little bit larger. And the line is the polynomial that we use for correcting the wavelength solution for the correct calibration. How it looks like? Well, this is what it looks like. It sounds horrible, but this is, for example, the old calibration. That line, and when you compare with the new calibration, better is again famous SMP LMC 058 planetary enabling. And when you compare the residual from the old and new calibration, looks an improvement. Well, what you can do with that? Well, what you care essentially. Well, again, this is one spectrum. Since LRS uses the full array, the sensitivity is fantastic, and so you can observe objects at C of 12.3 and get the spectrum and actually see the rest wavelength of oxygen 3 and H alpha. And so that's one of the reasons that we would like to do as much as possible the wavelength calibration. But it can be done. Impressive. Wide fieldless spectroscopy. This is a new mode. It's coming in cycle 5. It uses again LRS, the low resolution spectrometer. But the idea now is that we disperse the light across the entire full array. And so it has the same issues. The calibration essentially is the same, except that, as Anton mentioned, for the Grissom from NIRCam, you do have to be careful about. You need to understand the trace essentially along the entire full array so that you can correct it properly. But it's looking good. Still, we have, just as LRS, for the short and longer wavelengths, the same issues that we have. But it's going to improve. Time series observations. Again, they rely on LRS and have been used a lot. One of the discretionary programs. See this, I jumped it. I don't know why it changed, but MIRI in particular is supporting the JWC Rocky Wars director discretionary program that there are 500 hours of MIRI and HST. A lot of the observations are done with MIRI at 15 microns photometric observations. And again, one of the things that I want to share with you first is the stability can be reached by MIRI imaging by our observations at 15 micron. And this is a plot of the position in X and Y of the source by hours, and you can get essentially stability of the order 0.4 pixels or 0.004 in the observation. And what you get is, well, in this case in particular, this is an article from Quail that shows that in this case, JJ29B doesn't have an atmosphere, right? Which is one of the goals of the Rocky Worlds program, and try to observe these objects and see if we can detect an atmosphere. And then in particular 15 microns in this case, it sounds like this. No, that's a black body. Oh, I'm going fast, isn't it? But I can show you something in the back. So, and you can ask, it's not the question that you asked, Anton. It will be also very good to ask. So the calibration has improved tremendously since commissioning. And of course, the level of calibration that we have is enable a wide range of new science at the mini-infrared wavelengths. We have identified several aspects of the instrument where still we can enhance the performance. And those comes really at the level of improving the detector readouts and improving also the way we do flats, and improving the darks, improving the flats and readouts and so on. Since I got time, since I went fast, let me show you this. One of the things that Anton also mentioned is the background, right? And the background for MIRI is particularly an issue, in particular when people want to observe very deep observations of very dark. Because now it's not an issue in the sense that we learn from ground-based. In ground-based observations, you know, we look, people have known for a long time that you look in the mid-infrared, even in the near-infrared, if you want to take a precision observation, you need to look at the background. You have an off background observation and the target observation. So it's not as bad. But I want to show you, this is the trending that was done for the imager of the background. And so the color points are essentially the measurements that come from all the science data that we have. The dark points come from a dedicated program that looks at a very dark region to see what the variation is in the background. And so you see as few measurements for certain filters because we just start the calibration for those filters. But if you look, for example, 25 microns, first, if you look at the level of Megayaskit per steradian at 25 microns, just the background itself, because mostly from the telescope, the sky at that wavelength is of the order of 100 at most Megayaskit per steradian. The background is of the order of more than 900 Megayaskit per steradian. In the darkest region that we're observing, compose very well. So when you observe, for example, at 24 microns, one of the recommendations with the imager is that you also, just like in the ground, one takes an off position, background position, and subtract that, so you can get a good photometric calibration of the target. Again, same issue for 21 microns, but once that you go to 5 microns, 5.6 microns, the background is small, but it's still of the order of 1 millimeter. And so again, if you really want something high precision, one of the recommendations would be to do a background observation. This is for the imager, but we do see the same behavior for the MRS. For MRS, again, it's a function of time. It does look at the background increasing for the longer wavelengths, and a lot less flat for the shorter wavelengths. So indeed, the recommendation for good MRS observations, in particular for no point sources. For point sources, you can try to use the background that is in the field of view itself. But for extended emission in particular, we recommend always to have a background observation so that you can correct that. Friendly. And I think with that, I covered what I wanted to say.